Hello everyone and welcome to the Symposium of Team 38. The topic of our presentation is Neural Artistic Style Transfer. My teammates are Ramnik Bansal, Scott Stanley and myself Sushant Sarangi. So this is the outline of our presentation. We'll start with the definition, problem statement training, extraction of content and style characteristics, loss function, our model, hyperparameter tuning, results, and conclusion and future scope. Neural artistic style transfer not only limits itself to the transfer of images, but can also be used for creating music as well as for online shopping experiences. But for today's discussion, we'll only focus our topic to the artistic style transfer. The concept of neural artistic style transfer is motivated for creating unique visual experiences by combining the style and the content of another image. Basically, here we train the network to understand an image and produce the images accordingly. So for this implementation, we are using convolutional neural networks because convolutional neural networks are known to perform powerful image processing tasks. They contain feature maps or kernel that help us to identify various characteristics of an image. In neural artistic style transfer, we are going to use these feature maps of pre-trained convolutional neural networks to identify the style and the content of an image. The generated image is known as the pastiche. The objective of this project was to to use the concepts that we studied in EC 542 and implement a neural network and train to produce high perceptual quality images. Now I would like to invite upon Ramnik to carry on further.
Hello everyone. So let's carry on with the training of such neural style transfer networks. Basically, we have two subproblems here: extraction of content and extraction of style characteristics. One thing to note here is that training for artistic style transfer does not involve changing the weights of the given network. Rather, we try and manipulate the input image pixels to represent the style image. Extracting content characteristics. Basically, we use initial layers of the model. So because as they are very close to the input to preserve the characteristics of the input image or the content image. The activations of these early layers are saved for the content extraction during a forward pass. We compute the loss in terms of mean square error between the input and the target, where target is the content image itself. In this part, we are basically trying to learn the borders or the outlines of an image, which are the features and not the style of the content image. Here we can see we have an input image, and correspondingly we are see on the right hand side there's some lines that outline the structure of the given buildings in the image itself. Extracting style characteristics. In order to extract style characteristics, we compute the gram matrix. Gram matrix is nothing but the dot product of a flattened feature vector of a convolution feature map with themselves and the feature vector itself. We basically try to minimize the mean square distance between the different gram matrices itself. For example, let us consider the case of VGG16. So the activation values from the 7th layer generates the feature matrix of this order, and we flatten each of these feature maps and we get a vector of a certain length. Here we can see the basically computation of the previously discussed layer of the VGG16 network and the corresponding lengths of the feature vectors. In the end, you can see gram matrix is nothing but the dot product of each element of the matrix. Here Cij represents correlation between the different channels I and J. On the left hand side here, we have the style image, and on the right hand side, we can see we have extracted the features of the style image. Now we have the loss function. In order to make sure that generated image only inherits style information from the style and content information from the content image, we add the loss of both the computations itself. But since their losses might be out of scale, we add the weighted losses where alpha and beta represent the weights. They can be also termed as the learning parameters, and the total loss is mentioned as follows, as given in this formula. Now, like every other neural network, during each iteration, we have a given set of images. But here we have 3 input images: the content image, the style image, and the generative image. They are all passed through the network model, and they are iterated upon together, and the output image is generated till the user is happy with it. The value of hidden unit activation that encodes feature representation of the given image at certain layers are given as input to this loss function. The training starts with randomly initialized weights, making the image look like a matrix of random noise. With each iteration, we change the generated image to minimize the loss. Now I would like to invite Scott Stanley, our third teammate, to carry on forward.
Hi there. So for the baseline model of our artistic style transfer, we decided to go with the VGG16, except we're omitting the fully connected layer part because we're not trying to categorize the images we feed it. We're just trying to extract certain characteristics from it. So the two tables there show um, just the layers with max pooling and then the layers with average pooling. And for our model selection, on top of the VGG16, we also chose VGG19 and ResNet 50, which is a work in progress to try to see what other pastiches would look like with other models. So for the hyperparameter tuning, a lot of this is kind of subjective because it's a matter of figuring out what looks best, which can't really be expressed numerically sometimes. So in terms of this implementation, we're looking at the difference between max pooling and average pooling. We replaced max with average because it just looked visually better. The other one was the amount of iterations that we wanted to try to train our model with. Kind of varied between 10, 20, and 40. Another big thing were the style weight and content weights. So later on, you'll see images with style weight of 1,000, content weight of 1, as well as the style weight of 1 and the content weight of 10. Another thing in terms of tuning was the loss optimization. We used a limited memory version of BFGS algorithm, which was how we were able to minimize the loss between the style and the content. So these four results show on the left side was VGG19, the top involved max pooling, and then the bottom was average pooling. On the right side was VGG16 with max pooling, and the bottom consisted of average pooling. And then these results here show the difference in weights between weighing more towards the style and then weighing more towards the content. Um, as you can see, if styles weighted more, you see less of the content, more of the patterns, and vice versa with the content. And then these show the progression. As you increase the amount of iterations when training the model, you start to see more of the content, more of the style, and that's just proof that the loss between the style and the content loss is slowly going down as you iterate more and more up to a certain point. So in conclusion, we decided that the VGG16 coupled with average pooling was just the most visually appealing to us. Once again, that was just subjective. Some really cool things about this sort of style transfer is that it's not limited to just art. It can also be extended to music and other forms such as that. Um, for future scopes, some other things that could be done with this technology is working on color preservation. So the style doesn't override the colors and the content image. Another thing would be transferring multiple styles onto the content image, and then lastly, style interpolation. So that'll conclude our presentation on neural artistic style transfer. Thank you for watching.
Thank you.